what I will do, and I would say this is probably different than every other seminar we've had in the series so far, is really just talk about the ALCF, how it's positioned with inside Argonne, maybe a little bit about Argonne for folks that don't know. Um, and then a little bit of introduction to Aurora, some of the science that's happening there. But people should stop and ask questions along the way. So this is really kind of a infomercial, more so than a technical talk per se. So um, Argonne's been around since the Manhattan Project. It was, of course, a part of that whole build out in support of the war. Uh, really coming from the work that Enrico Fermi was doing at the University of Chicago, and the idea that doing that work in the major city was probably not a wise idea. Over time, it slowly moved itself out of the city, stopping in Palos Park for a single reactor before reaching the Lamont site that's been there ever since. It was very much a single purpose lab, kind of like a Fermi lab, in the sense that it was focused on nuclear power at its formation, but then over the last 50, 75 years, it's transitioned to one of the three large Office of Science general purpose labs. And Argonne has a wide set of activities that happen in it today. It's really focused around discovery. It's really focused around collaborations, and I think this is something that the national labs are extremely good at is collaboration, and it's something that, as I've spent more time, and I spent 10 years on faculty at NIU and now my second year at UIC, the labs really kind of pull together groups of people to work on big projects, much more so than you really see in kind of a university setting. The other thing that I think is neat about the national labs, and of course, Fermi Lab's a great example of this huge user facility, but the national labs large scale user facilities are a tremendous resource, and Argonne has a number of them, and I'll have a slide about that in a second. Just a little more on the lab. Probably about 4 or 5 years ago, we crossed over to more than $1 billion worth of budget each year. We're about, this is getting close to 4,000 now. About half of those are PhD scientists. We see a number of users come into the user facilities. And at Argonne alone, we have 6 of these spread over the Office of Science and Office of Nuclear Energy. For the students that are on the call today, there's tremendous opportunities, both at the undergrad, graduate, and postgraduate level. And feel free to reach out and ping me. We're a little late. I should have given this talk 2 months ago for the summer internships. Most of those are full now, but it is a great place to spend the summer. We bring about 200 students in grad and undergrad just in the computing alone. The lab is big. As I said, it's about 4,000 people, and it tends to work not on individual PI projects, but in overarching big areas. And so on any given year, 5 years, 10-year scale, our strategic initiatives, things that we are centered around, varies. I think this is kind of back at a high. We kind of go through a lot of them, and then it kind of weeds some out, and then we come back again. Things that computing is directly involved in are around the AI for science, autonomous discovery, some in the climate action space, stuff around image detection and of signatures have computing components, but then other areas of the lab focus on other things. I mentioned these user facilities, and I kind of wanted to come back to these because I think these are truly unique about the DOE system. And so, like I said, we have 6 of them at Argonne. The advanced photon source is probably what we're known the most for. It's an X-ray source. It's currently shut down. It should become operational again. Maybe we can get first light next week even. And it's going to come back. It'll be about 500 times brighter than it was before. It's a strong partner of the computing side, which we'll spend most of the day talking about. Atlas is our Argonne's tandem linear accelerator. It's been around for a long time. Of course, we're going to talk about ALCF. Attached to the APS is the Center for Nanoscale Materials. Lots of things around materials research, connected to the Advanced Photon Source and a number of other instruments. ARM, or the Atmospheric Radiation Measurement Facility, is a big multi-lab effort. We're responsible for the Southern Great Plains Station, and it's full of LIDARs and radars and other high-end climate sensing devices. It's about 200 acres in the middle of Oklahoma. ARM project as a whole has a number of mobile facilities that get deployed, and these are all gathering data about the environment and climate. And then lastly, the intermediate voltage electron microscope is the last little user facilities at Argonne. And these are not just resources for Argonne. They're not just resources for Illinois. They're not just resources for the US, but they're actually international research facilities. And we see, like we saw earlier, several thousand people come through and use these. And again, people should feel free to stop and ask questions along the way. The other thing I think that's really nice about the national labs is it does partner up with a lot of industry. And this is just a sampling of what goes on there. All right. So let's start to get into the computing space. Argonne is organized very much like a university with colleges and departments. At Argonne, they're called ALD-ships. Associate laboratory directors oversee them. They're kind of the equivalent of deans. And ours, Computing, Environment, and Life Sciences, is where 95% of the computing research at Argonne happens. And one of the things that we did about maybe 5-7 years ago is we greatly expanded that. It used to be the Mathematics and Computer Science division for decades. When the ALCF came along, there were 2 computing divisions. And then, like I said, 5-7 years ago, we formed the Computational Science Division led by Salman Habib, who's a computational cosmologist, and the Data Science and Learning that's led by Ian Foster. And what that did is that actually greatly expanded the ears that we had kind of listening and driving stuff forward in the computing space. And I think it's been very instrumental in Argonne's continued growth in computing. These are the individuals that are largely responsible. Rick Stevens is the ALD overall leadership. Valerie Taylor is the director of the Mathematics and Computer Science, where most of the basic math and computer science research happens. Ian Foster, who I mentioned, Salman Habib, and then myself. And then we are supported by a great set of deputies along the bottom here. All right, that's enough background. So now I'm going to talk about the LCF. So for those that have been around and interacting with DOE for a long time, they'll know NERSC, which is the National Energy Research Supercomputing Center. It started off in the Fusion Science Office, been around since the 70s, and it supports all of DOE's capacity computing. So if you have DOE funding, and you do computing, you likely make use of NERSC. That tends to have a lot of users that have a variety of different computing needs, from one node to hundreds of thousands of nodes. Around the early 2000s, the world was shifting in terms of computing. The US had dominated computing for decades. The top 500 list, which ranks the best and fastest computers in the world, was full of US-based systems. And then around the early 2000s, Japan put a machine on the top 500 in the first spot, called the Earth Simulator. And that caused quite a stir that the US, was so far behind in this, and caused for this congressional act And out of that came the Leadership Computing Facility. And when I say Leadership Computing Facility, that is one facility, but it has two sites. And one is at Argonne and that I direct, and the other is at Oak Ridge, and is currently the home of Frontier, which is the fastest machine in the world. Leadership Facility differ from NERSC in that it is focused on capability computing, and kind of the perfect scenario that, what was envisioned when these were stood up is that there would only be 4 or 5 projects at each site that consume all the time all year. Now, it's not quite that way, and I'll say a little bit in a minute about how many users we have and how many projects. But the idea was that these machines would be used for extremely big science that required most of the machine for significant amounts of time. All right, so um, so how are we organized? So the LCF is um about 130 people. So it's a big facility. It's organized into 3 pillars. One pillar is exactly what one would expect. It's a operations they run the machines. That's their sole responsibility, is to take care of running the machines. In that, you will also see let me see here if I can actually annotate along the way here. So we also, it turns out you can't go to Best Buy and buy some of the software that we need. So we have an advanced integration group that is responsible for building software. And this is not glamorous word processor or Photoshop, but this is things for like around large scale accounting of users and their allocations on the machine. We also, since I've taken over the facility, and I've been directing the facility for about 20, no, 14 years or so. We've established a business intelligence. These supercomputers generate vast amounts of log data that we mine. And then you have the kind of the traditional things that everybody's expecting in terms of technical support and HPC infrastructure and storage, our tier 1 support, and they all fall under this director of operations. The second thing is these machines are unique. And so this group, the technology group here, is really well versed at eking performance out of the machine. So we have 2 performance engineering teams. People generate lots of data, so we have a visualization team. And these are 2 new areas here. AI, which you may or may not have heard of, it seems to be taking over the world. A group in AI, and I'll say some more about that in a bit, and data services and workflow, and I'll also say some more about that. And these are pretty exciting growth areas here. The last thing I'll say about the LCF that is really unique is the fact that we have a 3rd pillar organized around science. And that group is PhD domain experts in materials, energy physics, climate studies, and they're partnered with our user base to help further their science. They are experts in the hardware we deploy, but they are also experts in domain science. And I think that is something that you won't see at many other user facilities, supercomputing user facilities. Some places will have application engineers that kind of help a little bit, but not at the scale that the LCFs do. And at Argonne, they're called catalysts, and at Oak Ridge, they're called liaisons. All right, let's see if this is going to work, that I can change screen up and look at that. It doesn't go away. So much. I'm blessed to work with some of the most exciting hardware, but when it comes down to the end of the day, it's this group of folks that we see in front of us that really make the facility what it is. I think this has all last year's students also in the picture here, but like I said, we're about 130 with students, maybe we even get up close to 150 that really make the facility work. We support all but six states, I guess. In the US, we have an international user community. On any given year, and you've got the numbers here for 23, in any given year, about 50% of our users come from universities, the academic community, about 50% come from government, labs, and the like. About 5%, and this is actually last year, looks high in terms of industry, about 5% from industrial users and about 5% from international use, and we don't have that listed here. While we had 417 active projects on the machine last year, most of those are discretionary allocations, and I'll say a little bit about the allocation program in a second. The big projects are the significant consumers of that 35.7 million hours of production compute time. All right, so a little history here. As I said earlier, the facility was established in 2004. Our first system was a IBM Blue Gene L. We consider it so small it didn't get a name, so it was just known as the IBM Blue Gene L. That quickly gave way to Intrepid, which was the first of our Blue Gene series systems, a Blue Gene P, and it came in at about a half a petaflop of performance. A few years later, it became Mira, which was a 10 petaflop IBM Blue Gene Q. Argonne was very much focused on many core architectures. And again, we remember the LCF is one facility, two sites. Oak Ridge were heterogeneous computing, CPU, GPUs. We were taking an architectural diversity and doing many core CPU only systems. The world kind of looked like it was well positioned for that path. IBM decided to end the Blue Gene series, but Intel kind of quickly took up the mantle of large many core systems with their Intel Xeon Phi architecture. And so our path from many core with IBM was to this architecture, and the initial machine was Theta. Theta just was retired this past December, December 31st. We shut Theta off. It was about a 10 petaflop, 11 petaflop Knights landing system. Its follow-on system was planned as a Knights Hill, and that would have been the original Aurora. And that would have come in about 2018 at about 200 petaflops. Intel decided to end the Xeon Phi architecture. And so at that point, we pivoted. And that was unfortunate because we would have loved to have had a 200 petaflop system in the 2018 timeframe. But it also gave us an excellent opportunity to push towards exascale. And with DOE Oscar support, we pivoted to Aurora, which is the system that we're currently standing up. In between there, we deployed Crux, which is again, large homogeneous CPU-only machine. And we deployed that largely to better understand the architecture of HPE and the system that would eventually be Aurora, and Polaris, which was our first large-scale heterogeneous system. So this is about a 44 petaflop CPU GPU system. During the pandemic, we added Theta GPU in 2020. This is a pure CPU system that got attached to Theta, a pure GPU system that got attached to Theta, and really was there to support research in support of COVID and trying to understand that better. And of course, we're on this path to Aurora. Along the bottom of this slide, there's a couple of things that I point out that's maybe of interest to some folks. One is JLSE. So Mark Sneer, who was the division director of Math and Computer Science Division and a professor at Champaign-Urbana. And I established JLC in 2013. Um, and really, it's a zoo of latest and greatest in hardware. And it's a great place to test things out and try new things. And so we have some like Grace Hoppers are in JLSE that we're starting to experiment with. As I mentioned earlier, this AI test bed or AI thing was taking over the world. And so in 2020, we established the AI test bed. And what we've been doing there is we've been working with AI startup companies to evaluate hardware and to specifically evaluate their hardware for science and engineering problems. For any of the other old gray-haired folks in the audience, you might remember in the 90s, early 2000s, we kind of had the same boon with the advent of the GPUs. You went from kind of the $100,000 SGI reality engines to commodity-based GPUs, and there was, I don't know, dozens of startup companies making them. And of course, that world is shaken out, and really we're left with NVIDIA, AMD, and Intel. And then lastly, we were doing some work around edge computing with our edge test bed. All right, so some interesting things around Aurora. So it is expected peak performance. So this is the theoretical. If you add up everything that the machine can do, that it will be in excess of 2 exaflops of double precision computing. We're more likely to see, you know, in kind of a sustained performance space, 1.3, 1 point, maybe as even high as 1.5 exaflops of performance. We're still working towards this. This is a hybrid system, CPU, GPU. So every Aurora node, and there's more than 10,000 of them, is 2 Xeon CPUs and 6 GPUs. Now, of course, and maybe we don't notice this that often, Intel's actually been building GPUs longer than NVIDIA, or as long as NVIDIA. They're just often embedded inside, they are embedded inside the CPUs that we buy from them. So this is Intel's move to discrete GPUs. And so we have over 20,000 CPUs and 60,000 GPUs that we need to kind of manage within the system. The system is connected together by Slingshot interconnect that gives us high communication from node to node. We have a peak injection rate of more than 2 petabytes per second and a bisectional bandwidth of greater than 6.9 petabytes per second. This is all connected for fast storage to a DAOS. This is something that Intel's developing. This is a distributed asynchronous object store. And we have about 230 petabytes of storage here. This is all solid state and very fast writes to that. And then our global file systems sit behind that in terms of connecting to other parts of the facility. In terms of how this gets put together, I've mentioned some of this stuff already. We have a compute blade. These are about maybe 1.5 inches or so thick, 18 inches wide, maybe 3 foot deep. They weigh about 100 pounds. Those get turned on their side and slid into a rack. For every so many compute blades, we have a switch blade that those connect into. You assemble the compute blades and switch blades together into a rack, and we put those together in the Aurora system. I come back to this picture here. So this is Aurora. This is the first row of 8 here. These, I guess you can't see it. I'm wiggling my mouse here, but these here are the compute racks, and the blue and red tubes here are hot and cold water. So blue, cold water coming into the system, about 80 degrees Fahrenheit, comes out on the red tubes about 90 degrees Fahrenheit. For every 3 compute cabinets, we get 1 virtual cooling unit, and this is really just kind of where the water management happens. And then the plumbing for Aurora is the water goes under the floor of this 4-foot raised floor, and all the electrical sits above it and comes right down from the room above. All right. I like being able to annotate, but it's kind of awkward switching back and forth. Um, oh, actually, I should have just gone to the next slide. I had some pictures here. So like I said, this is the first row that we were seeing. All the people were standing, filling that space. This is down between 2 rows in the lower left-hand corner here. They flip back and forth, and there's a total of 8 across the space. I should have actually put some pictures of the mechanical because it's quite amazing. For when I first started kind of doing this, for every square foot of floor space that we put computers on, we kind of planned for a square foot of mechanical space, plumbing, cooling, electrical. Now it's kind of shifted to it's more like 1 for computing, 1.5 for electrical, plumbing, mechanical, maybe even getting close to 1 for computing and 2 for behind the scenes stuff. It says something about the density at which they're packing the machines, and the amount of infrastructure you need behind the scenes. Aurora doesn't have CUDA. It's a GPU-based system, but it relies on SYCL for that connection to the GPUs, and OpenMP. HIP is AMD's kind of equivalent of a CUDA, and we also support that on the system. And then a number of higher level systems like Cocos and Raja are also available. CUDA is not, and this is one of the challenges that people have in front of them with large GPU codes and moving to Aurora. They have to do that translation. What I will say is both SYCL and HIP are open. Well, SYCL is a standard. The Kronos Group oversees that standard. And so once you kind of move, you can run SYCL code on all 3 GPUs. So there is some advantage to moving off of proprietary CUDA to a more open standard. And just some early results. So I grabbed this slide from Hassan Habib's group. And this is what they're seeing just on initial Aurora performance. So if you kind of look at an A100 NVIDIA system as the baseline, there's HIP implementation on the AMD MI250, which is the heart of Frontier at Oak Ridge. It performs a bit better. And then where we're at with SYCL on the Intel PVC. PVC is a code name for the GPU in Aurora. You see where we're at from that. And so we have a number of codes that we use in the early days to kind of benchmark and help tease out the state of the system. Aurora, while it's our kind of singular focus right now, is part of an ecosystem. Polaris, as I said, is our current production resource. That Theta GPU, that DGX-based system, when Theta got retired, Theta GPU got renamed to Sophia. This will largely be an AI development system. I mentioned JLSE and the test beds there. You can see the variety of different nodes that we have there. And of course, then our global file system, we have 200 petabytes of spinning disk. All right, so this is interesting. And there's some very neat work going on the AI testbed. So right now we have 4 systems that we consider production research testbeds. What does that mean? That means anybody on this phone call, Zoom session, can get access to them. They're open to the world. We have the 2nd generation Samba Nova system, the SM30. We have a new Graph Core Bow based system. We have 2 CS2 Cerebrus machines. Each of these are unique in their own way. The Cerebrus system, of course, is that 1-foot wafer. And then lastly, we have a new Grok-based system. We also, behind the scenes, have a Habana, and each year we kind of acquire one or two new systems. We do this through a phase of where we buy kind of a node, and we see how that node performs for scientific workloads. And then we kind of scale that node up to maybe a handful of nodes to just see how it scales and works in parallel. And then these larger systems here kind of made it to the next generation where we bring them into production, open them up to the user community, and they're really kind of at the larger scale. These are not your mother's computers, and so they do take some getting used to. And what we've kind of seen early on is somebody will have a really innovative hardware and they won't have a great software story, or they'll have a really great software story and they won't have really interesting hardware. And so we spend a lot of time trying to get the community spun up, and we're just wrapping up. It's either this week or next week. We do an 8-week, 1 day a week, 2-hour online session for AI for Science. So trying to connect AI and science and engineering. During the summer, and these 4 that are listed here, I encourage folks to look at them if they're interested in this space. We do a 2-day, about once a month workshop on the specific hardware that I mentioned. We try to record everything, so a lot of this stuff can be found on YouTube, on our YouTube channel. But I know the 2024 AI training workshops are, I think the posting just went up. I actually might even have linked to them on the C2P2 website. These are 2-day sessions, really where folks get specific direction on how to make use of this hardware. I've already said a bunch of stuff about staff and how we are organized. Let me say a little bit about allocations, and this is maybe more aimed at the professors on the phone call than some of the students. These systems are open, open to the world. Insight and ALCC are extremely competitive allocation programs. They're similar in scope to writing an NSF proposal, and you get those hundreds of millions of hours of compute time. They're great to win. They're useful for getting work done. But I wanted to actually kind of point out the director's discretionary program. And this is a fairly lightweight program. It's about a paragraph to a page of text. And what you're trying to just tell in this story is you need to make use of these big machines. And in doing so, then you can get anywhere from 3 to 6 months of time on these systems. And the goal there is to actually do some strategic exploration and or prepare for the other 2 big allocation programs. But people often think, oh, these resources are outside my range. And what I would say is they're not. And I would also say in the case of the AI testbed machines, those are really aimed at folks to have some exploration. So I encourage people to look at them. All right, so this slide I usually can give an hour-long talk on by itself. And what I like to point out in this slide here, going back to 2004 when we started, you see the first line there of hours. This is time we allocated to the user community. And around 2019, 2020, we moved from core hour allocations where we were up to close to 6 billion core hours to node hours. And some of this has to do with the hybrid nature of the CPU, GPU, where we could no longer just allocate a single unit, so we allocate at the node level. That's why you see that drop back down. Still a tremendous amount of capability in the system, but this is at the node level around the 71 million. Along the bottom, the next line below that is the projects, and you can kind of see this ramping up as the LCF got going, and then you would see this steady state where we kind of bounce up as high as 69, and then it kind of goes down, and then it kind of bumps back up, and then it kind of goes down. And really what you can see is those numbers that jump up is really when a new set of capabilities were entered the system. Lastly, and kind of the picking up the pace here, is what I would say is different about the LCFs as opposed to buying a machine for a specific domain is the variation, the variety of users we have. And when we design the machines, trying to take into consideration all the different demands. But this is just a sampling, and this is just a sampling of publications going back to 2008, the quality and variety that we see, from your traditional phys rev and science nature to high end for like supercomputing, getting papers into the supercomputing conference and the International Journal of High Performance Computing. So you see a wide variety here. All right, so what happens on the machines? So we see things all across the board on all different domains, from universities to national labs to industry, driving what we do. As we look forward, and I'll have some slides about this in a few seconds, while we're still standing up Aurora, we're starting to look at what the next machine needs to look at, ALCF4, and with that, what's driving that. And one thing that should not be surprising to you as you look at the list here of 4 or 5 science examples, you'll notice AI and real-time data moving its way into that story, that description. Traditionally, these machines were used for modeling and simulation, but more so, all the way back to even Mira, we've been starting to design them to support not only modeling and simulation, but data analysis, data science, and AI. So kind of talking about the last 2 areas of interest that I think is interesting, we'll wrap the talk up on, is this data science, data processing, and AI. And so within the DOE, this integration with experiment, integration with real-time needs, it now has a new term, and it's called IRI, or Integrated Research Infrastructure. I just called it fun science for a long time. But it should ring true with the high energy physicist here, in terms of needing vast amounts of computing power to analyze data, not only as it comes off the detectors, but immediately afterwards in a timely manner. And so we've been supporting all the offices within the Office of Science in this effort, from HEP to fusion to the basic energy sciences, with their light sources. And so around this IRI, we're trying to figure out how you take a machine that's traditionally uses a batch queuing system. So think waiting in line at the grocery store or the airport is how you gain access, right? You submit a job, you wait for your turn, it runs, you get your results when you get your results. Well, it turns out that experimental science is not well tuned to that, right? So when the advanced photon source is collecting data, they want to know information about that data. They need to do so in kind of real time. And so a great example of this, and this goes back to 2018, is some work that we did with D3D, the tokamak at General Atomics in San Diego. They do an experiment. The shot lasts a super short period of time, and then the system basically resets and gets ready for the next experiment. And so in that case, as they were doing this, they set up an experiment, they run the experiment, and then the experiment happens in just a split instance here. And then they start getting ready for the next one. They have to do all the analysis. And with their local machines, the analysis always bled into this next setup. And so this setup number 2 is not informed by the results of experiment 1. And so what we did is we worked in real time with them to immediately ship the data to the ALCF, do the analysis in a much shorter time, allowing them to influence the next generation. And we see this time and time again. We see this time and time again. So the advanced photon source has exactly the same thing. And while that General Atomics example was a lot of hand holding and swinging of, a chicken and maybe hopping on one foot to make it work, we've worked very hard over the last year and a half to automate this. And now we have infrastructure in place that kind of a human out of the loop, we can interact with running experiments. And this no human in the loop is a great example here at the advanced photon source that we did just before it went into its year-long dark period for the upgrade. All right, so I'm going to talk a little bit about AI, a handful of slides here, and then a couple future slides, and then hopefully we'll be done on our 1-hour slot. So what I wanted to capture here on this slide is just the vast amount of scientific activities that AI is working its way into. And we're seeing things in terms of just drug design that's moving us from kind of the computational simulation space to a much more interactive, rapid processing through that space, to things around imaging science and things coming out of experiments like those happening at the APS, tokamak, protein folding, Monte Carlo for reactor simulation. So we're seeing AI working its way into a number of things, and it's working its way in a couple of different manners, from helping pre-select areas of interest to replacing extremely complex components of the computational process or surrogates with AI driven ones. And so we are, in foundation models, Aurora or ChatGPT, and we are working on something called Aurora GPT, really looking at how they can enable science going forward. One of the things that I think is interesting, having been at the lab for close to 30 years now, the discussions of ethics within the DOE and ethics around AI is very much an active activity, and I think as it should be. I think the other thing that's interesting about what AI is going to do to supercomputing is it's going to bring people that were traditionally not supercomputing users to the supercomputer. And so that has some interesting consequences. And those consequences are, these machines are not the most user-friendly. No one ever does human user studies in DOE around usability, productivity. And so I think these things are going to change. I think this notion of batch queued systems is going to give way to a much more interactive, engaged. And so I think the future is pretty exciting right now with respect to this. I started to mention this, that we have this thing called Aurora GPT. This is a large foundation model, really focused on science and engineering. And we've started this project. It's really focused on being supported on top of Aurora with a handful of partners from some universities and other institutions, really looking at how we do this for the scientific community. And so this year we've been working on text-only models, moving on to more multimodal ones in the out years. There's a 3-year internal investment that the lab is putting in place. And what's neat about this is if you start to look at like what it takes to train something like ChatGPT, it's a supercomputer. These are what, Google, Amazon, Microsoft are investing in, right? So Frontier is the #1 fastest machine in the world. Aurora is the second fastest. We benchmarked last November with about half the machine operational and got the #2 slot. The #3 slot is a Microsoft Azure-based system called Eagle, and really put together in support of their partnership with OpenAI. And so when you start looking at model size and token counts here to train these large foundation models, we're talking about, not insignificant amounts of time. So if you look at kind of a 7 million parameter model, that's 21 days of all of Polaris. Now, you take that and you move that over to Aurora, and that's about, a little over a tenth of the day, 15% of the day, a couple hours, 3 hours or so. But you get down to this bottom where you start looking at a trillion parameter model, and to train that, it's 200 days of all of Aurora's use. And so the question is, is every domain going to build their own model? So we're already starting to see these collection of expert models where you train some base model and then you train some smaller models that are experts in a given domain or given area, and then you have them work together. It's a rapidly evolving space. But the one thing I can say is that supercomputers will be at the heart of the future of AI. And so that's very exciting for me. It's a little job security. All right, 2 more slides left. Where are we going? So traditionally, and these 2 slides come from a talk that I just gave to the advisory board of Oscar, the ASCAC, subcommittee on facilities. So the DOE every 10 years or so looks at each of its facilities and wants to kind of understand where they're going. So for me, it was a great thing to force me to sit down and think about and put on paper where we're going to go. And so I thought it was worthwhile and interesting for the conversation today. I really would like to see ALCF. I would like to see DOE computing transitioning to a much more dynamic, evolving system. What does that mean? When we acquire systems like Aurora, that is planned usually over 5 years till it arrives, then we stand it up and we operate it for 5 years. And then kind of that 8 to 10-year window, you're in a pretty rigid structure, right? So like there were no AI accelerators available when we started planning for Aurora, very much so when Oak Ridge started planning for Frontier. And because of the rigid structure, there wasn't very much opportunity to actually integrate those into the system as we moved forward. And so one of the things that I would like to do, and this is a kind of a combination of both technology and social change, is move computing from this notion of a very rigid, hard-coded facility to something more dynamic, and where we're able to upgrade at least components of the system on a more frequent basis. And that's a challenge, because if you're talking about being production and at the same time you're changing the system, you have to figure out how to do that in the right way. And so we'll see how that plays out. Energy efficiency and sustainability is a huge thing going forward. So no one's asked any questions at all, but I'll just say that people often ask me, well, how much power does Aurora consume? We don't know yet because we're still finalizing its operation. But what I did bring to the building in support of it is 60 megawatts. Now, maybe this is not a big deal talking to the high energy physicists. I know when I was at Fermilab was already at, in the tens of megawatts of power consumption for the Tevatron and supporting infrastructure. So maybe this doesn't seem so big, but most people freak out when I say 60 megawatts. And so energy efficiency and sustainability is a key thing that we need to look at going forward as we build out Helios. If you look at the things on the right side of the screen, Aurora is what we're doing now. Helios is the next machine, and Panos is the machine after that. I want to use Helios as infrastructure to really get in and instrument codes, machines, machine room. Right now, compilers optimize for the best performance. What if our compilers optimized for the most energy efficiency, willing to trade off time for power use, or at least give the user a tunable setting there? Same thing holds true right now. We allocate time on the machine in node hours. What if I gave you a power budget? Would you change the way you code? Would you change your prioritization if those were your allocations? AI is going to be huge. It's going to be huge in a number of ways. It's already huge in surrogates, kind of pre-screening data, but it'll be very useful in helping analyze data, moving computing more towards this notion of a interactive microscope, right? I mean, kind of the days of going back into your high school biology lab where you're fiddling with slides and the microscope. I would love to see the supercomputer moving in that direction where you're much more interactively working with it. AI, I think, is going to diversify our user base. It's going to bring users that traditionally don't use HPC resources to the table to do new and exciting things. As always, I want to see more integration with Oscar research. This is the machine working research, as well as staying in line with DOE priorities. Just for information, this is kind of the timeline, right? So we've already gotten CD0. This is a DOE speak, but says that we have approval to start planning for Helios, and it will be deployed in kind of the 2028 timeframe. We're looking for, even while that's being deployed, starting to work towards Panos for deployment in 2034. With that, I'm sorry for just rambling on and on. Yeah, LHC. Okay, thank you, Hector. LHC is, I guess I can get a computer twice as big. LHC is 120 megawatts. So let me stop, see if I can see people. Encourage everybody to turn cameras on so I can.
So let me first, Mike, that was awesome. Thank you.
Right.
So I have a bunch of questions, but
Sure.
I'll leave to others first.
Questions?
If not, I can kick it off with a bunch of questions.
Sure.
So the simplest one is, do your new facilities then require new buildings, or do you use the existing infrastructure and buildings? That's the simplest question.
So that's a great question. So, and I'm kicking myself now for not showing the mechanical space for Aurora, because it's so impressive. So for Aurora, so all those machines up to Aurora lived in the same building, and the machine room is big enough that we just kind of had space to move things around, to fit everything in there. Aurora, the racks are so heavy that while we probably could have pigeonholed the physical machine into the space, two things happened. Well, one, the mechanical, the power and cooling requirements were so great that needed more space than we had dedicated to that. The second thing was the weight of the racks, and they're in multiple tons per rack, was heavier than the floor would support. So even if I could fit it into the existing machine room, I would have had to bust up floor and reinforce it. And for that reason, and that reason alone, we added on about 30,000 square foot of space just to the south of our existing machine room, but eventually knocked down a wall, and the machine room now looks unified. To house Aurora, we put all the power, so all the transformers and switchgear sit immediately above Aurora, and those brown or gray boxes. The power comes right through the floor, right into the bus bar that powers the racks, and then we bring water in from below. The machine sits on 4-foot raised floor. We have two 24-inch headers that bring 44,000 gallons of water in for cooling that feed off the cool the machine. So that was a long-winded answer to yes. Case there, I'm hoping that I won't have to build a new building for Helios. I'm hoping that we can just use existing space.
Good. And I see I'm not the only one with questions, so I won't ask my others. We'll go to, I guess.
I think Hector was up next.
Hi, Mike. It was really nice talk. I had a question. So you mentioned you have about a 5% of industry users, right? If I remember the number that you
Yep.
said. I'm wondering what type of projects from industry do you get? I'm wondering how the interaction between the for-profit, let's say, environment and the type of environment that we are working on works, right? So if this is reviewed, what type of process do you get? Those kind of things.
Great question. So let me just step back. So they have to meet the same requirements that the users do. And that being said, all access to this machine, all time on this machine is free. even for the industrial users, as long as they adhere to the requirements. And those requirements are that you're doing open science. And so from that standpoint, you do get some industry users coming who want to tackle basic science problems. The other thing I would say about the general industrial user base is it's big companies that have computational scientists on staff. And this is a little challenging because you'd like to see some smaller, I'll call them mom and pop companies, but they're not big enough to have people trained to make use of big machines. So who do we see? We see Pratt and Whitney, Procter Gamble, Boeing, GE Research. These are the scale users. And, GE Research has done things around just fluid dynamics, understanding the acoustics of jet engines. And this is I love about my job. Like they were just doing work on like how to do noise reduction on engines. And just by doing just general noise reduction, they could see 3% more fuel efficiency. And so they're doing work that they're willing to be open and talk about. They may not be publishing papers because there's not a lot of places to publish what they're, well, there is places to publish, but what they're doing is so specific that they don't, but they're willing to talk about what they're doing. If somebody is doing, and I've had a handful of these, they want to do something that needs the big machine that they don't want to talk about, they don't want anybody to know. And the places that I would say in the general space, oil and gas, they'll pay. We charge a full cost recovery. So we have some complicated formula that says, okay, here's what it costs. And again, it's still a win for them because there's not a lot of Aurora's frontiers in the world. So if they want to try something at that big scale, it's an easy way to try things out. So we've had a handful of those. Back to the allocation process, the discretionary allocations, pretty lightweight, pretty easy. The big insight allocations, which industry has been awarded, happen much the same way our proposals are reviewed for cash. We have internally, Argonne and Oak Ridge run what we call a computational readiness, making sure that they're big enough to ride the ride, right? So they're not doing something on their laptop and tomorrow wanting to do it on 60,000 GPUs. So we evaluate that, we give a score. And then the technical scientific portion goes to a review panel. We instantiate about 8 different review panels in the process that cover very specific domains. And there's about 8 to 12 different binnings with about somewhere between 10 and 20 technical members of the community, not at Argonne, that technically review and rank these, much like the NSF proposals or DOE proposals. We get back a ranked list, and then we do some work from that. Hopefully that answered the question.
Yep, that helped. Thanks, Mike.
Jack?
Yeah, can you guys hear me?
Yep.
Okay, hey Mike. Yeah, I love hearing about the ALCF, so thanks for the talk. I was kind of wondering, like, assuming 100% usage, which isn't really the case, like you mentioned like around 60 megawatts would be nice. How much of that would be like usage versus cooling? Is that accounted into like the cooling factor?
Yeah, so what I brought to the building is 60 megawatts. I'm hoping that I don't use 60 megawatts. Right now, we're ramping up usage, and we don't break it out. We will at some point, but right now, I just don't have enough infrastructure in place to tell me what each component is. But over the weekend, we were somewhere between 40 and 45 megawatts of power consumed, and that's both computing and back-end infrastructure. And so in that 60 envelope, it will cover both operations and cooling.
Yeah, thank you.
Sure. Rick?
Yeah, thanks, Mike. That's a really fantastic talk. I have a question which is similar to what Hector asked, and I think you answered much of my question. But if I were a student in C2, the P2, how would I go about trying to get some discretionary time on some of the computing facilities at Argonne?
So it's through this discretionary allocation program, and if I was a student, I would say what you really want to do is you want to partner with your mentor or faculty advisor, but it's really pretty lightweight. You write somewhere between a paragraph and a page of text outlining the problem that you want to do. The key thing is one that you have a idea of what you want to do. You just I want to log in. That's probably not going to fly, but I have some idea of what you want to do, but then able to articulate why you need something the scale of Polaris, why you need something the scale of Aurora. And so it's not toy problems, right? You're driving towards something substantial. That being said, in the case of the AI testbed resources, that's kind of the Wild West right now in the sense that we've got people that are doing, trying to understand how they can take maybe some detector code and move it from kind of the traditional compute space to an AI platform. And so that's less so about being at scale and more so being like an interesting problem. And I must say, all of our AI startup partners have been awesome to work with. I think they're just also, much like myself, fascinated by the idea of science being on their things because, of course, as much as we would like to think that we motivate the world in purchasing, we're not the big consumers compared to the business sector.
Yeah, okay, fantastic. So, in fact, I'm thinking of a particular project which one of my students has, and applying, trying to train transformers on particle physics problems, in particular event reconstruction. And he just needs like loads and loads of time to train these transformers, which are notoriously difficult to do. So okay,
Yeah, let's talk. I know you and I have some time scheduled soon,
Yep.
so we should talk more about it. But yeah,
Excellent.
sounds perfect. So, Jared.
Yeah. So I was looking up. So it's 120 megawatts for the LHC and Atlas, right? The experiment that some of us work on site. The computing, our big computing farm is 2.5 megawatts. Sort of sets the scale, but we are exceedingly close to that limit. So a number of us are focused on thinking about how to use FPGAs to solve a lot of the computing problems. And obviously, if you just want to have as much resources as possible, you don't care about power and the environment, and you just go ahead brute force with GPUs and CPUs. But that is the real way to reduce power consumption for many problems are FPGAs. So is there a thought to using? So I guess two things. One, do they exist at all in ALCF? And two, is there a thought to using them in any capacity in the future?
We have some FPGAs, I believe, at JLSE. Don't quote me on that, but we have in the past at least. The problem is, and I would say, high energy physics has been out in front of computing more so than any of the other domains, right? And so you guys are not scared. And so you'll take on programming FPGAs, but FPGAs are not straightforward to build stuff on. So as a general purpose facility supporting this wide space of users, that's been the problem, and that's why we haven't gone down that path.
And that's fair. And 3 of our students, I think one of the ones that Rick was talking about, and 2 others are, developing, tools using HLS, which these days is not simple, but is much easier. As someone who spent a lot of their graduate career writing VHDL code to program an FPGA is an awful nightmare. But now the tools are getting better, and so I was just thinking sort of the problem from the other direction also. If there are more facilities that have them, it sort of leads people to develop the expertise. So kind of goes.
I don't disagree. I think some of the other things we're seeing better ratios of performance to power on the AI accelerators in a lot of ways for at least some subset of problems. Not even just using those machines for AI workloads, but much like the early days of the GPUs, they were built to satisfy Hollywood and 14-year-olds in terms of their gaming. They weren't built necessarily with the mindset of doing science on them. But we're starting to see, and we have a handful of problems. And there was just a talk within the last month or so, and it's probably recorded on the ALCF site, where one of our postdocs, Sid Raskar, gave a talk about non-AI uses on AI accelerators. And so it may be worthwhile checking out. And, for those C2, the P2 fellows that have not defined a project yet, that might be something interesting to look at, like, a scientific workload, non-AI scientific workload on one of these pieces of hardware could be a cool thesis.
Yeah, definitely. And then I guess the other question, sort of following up on what Rick said, you and I try and spam everyone's email quite a bit. But are there particular trainings or workshops that ALCF hosts? Because the majority of them are like, you have this expertise already, let's help you sort of deploy it on our facilities. And so, you mentioned the AI one, but are there other ones that the students should look out for new?
I should be better at making sure that we get onto the C2P2 mailing list, more of the general purpose ones. There's somebody, one of the fellows has been doing the AI for science. I don't remember which one it was, but somebody went through that because I just saw the list and I recognized the name. And then I've been better at trying to keep the C2P2 website up to date with links, so people should just periodically check there. But I will try to do better.
Yeah, because it would be great, I think, I think a lot of students need a sort of starting point, it's one thing to write, a small program on your laptop and compile it with a makefile, but with thinking about how to deploy it on much bigger facilities is a scary thing, and guidance is helpful. Yeah.
Well, as the ECP, the Exascale Computing Project, wound down, we did do this last summer with Berkeley and Oak Ridge, a 1-week boot camp aimed at taking kind of advanced undergrads, new grad students into that space as rapidly as we could. We run a program called AppPesc, or the Argonne Extreme Scale Computing Program. It's a 2-week camp every summer. It's always in August. This summer, we'll just announce the people that go to it. But it's something else for the fellows to watch for next year. It's about 80 students, 2 weeks in residence. I give an opening talk after dinner on the first night of the 2 weeks, and everybody's smiling and they have bright, shining faces. And then I usually try to pop in at the end of the 2 weeks, and people are like all haggard because they go from 9ish in the morning, full day lectures, 9 to 5 on parallel programming, architecture, everything. They eat dinner, and then they have 2 or 3 hours of hands-on till 9 o'clock at night, and they start up the next day, and it goes 5.5 days. It's Monday through Friday plus Saturday morning, and then Monday through Friday the following week. And it's great. And you have to be young to survive it, because I couldn't do it, but it's a great program. And so something for people to watch for the call next year.
All right. So yeah, if you have ideas when it comes out, we can look for it, but it'd be helpful to forward on to everyone. So, okay, great. All right. So I think we are well over on time, but we had really good questions and I dominated a bunch of them. Do anybody have any last questions? So if not, thanks again, Mike. That was super.
All right. Look
All
forward
right.
to seeing everybody at the retreat this summer.
Yeah, we have to plan that still. Rick still owes me an email reply, so we'll iterate on it. So, yeah.
All right.
Okay.
We'll see everyone. Thanks.
Bye.
Bye.
Bye.